Behind me, you can see the value of the FTSE 100 stock price index. The price is updated roughly every 1 minute. And as you can see, as we're progressing through the afternoon, it's between 2 and 3 o'clock now, the price is evolving. Now, even though it is represented as a continuous graph, this value is updated every minute. In other words, we have a sequence of values during the course of the afternoon. This is referred to as a discrete stochastic process, or a stochastic process in discrete time, to be precise. All a stochastic process in discrete time is, if we're honest about it, is a sequence of random variables. Now, of course, these random variables are all connected to each other because they're the value of a financial asset as it evolves over time. So it's quite natural to think about these random variables in a way that links them together. Now, during the course so far, we've talked about random variables, we've talked about measurability, etc. And all of those notions apply directly to stochastic processes because they consist of sequences of random variables. One thing in particular that we need to look at when we look at stochastic processes, of course, is the fact that they evolve over time. So at each point in time, there is a past, consisting of things that have already happened, and there's the present, and there is the future, which you simply don't know yet. And in finance and in many areas where we apply stochastic processes, of course, the future is of great interest, and we try to model the future. But the one thing that remains is that the past can give us some information about various things. Now, the question is, how do we model this? And the answer is really to look at what we already know from random variables. Now, we know if a random variable is measurable with respect to a sigma field, then that sigma field contains all the information that I can get from the value of that random variable. To be more precise, even, every random variable generates its own sigma field, which contains exactly the information that you can glean from that random variable. And what we can do is we can take that idea and generalize it and make it apply to stochastic processes. So, for example, if you look at the graph behind me, at about 1:30, just after 1:30, there was a big spike in the value of this index. Okay. Now, at 1:30, we might have had some information about the value of the index up to that time and how it has evolved during the day. We might have wanted to represent that by a sigma field. Remember, a sigma field is a collection of events that you can, get information about whether events have happened or not. As we go towards the spike, of course, what will have happened is our information will have increased, and it will have increased, and then suddenly there was this burst of information about this spike having happened. Okay, and we represent this by actually thinking about it not as just one sigma field, but actually as a sequence of sigma fields. Just like we have a sequence of random variables, we can have a sequence of sigma fields, and as time goes on, these sigma fields are getting larger and larger because the events that I can distinguish between are getting more and more. Because as more things can happen and the possibilities increase, there'll be more and more events that I might know something about. And really, this is what the idea is behind the notion of a filtration, which is what I'm going to define next. Let X be a discrete time stochastic process in a probability space. Now remember, discrete time stochastic process is none other than a sequence of random variables. The filtration generated by a discrete time stochastic process is likewise a sequence of sigma fields such that for each time step n, the nth sigma field is the smallest sigma field with the property that x0, x1, etc. up to xn are all fxn measurable. this definition contains quite a few things that we can talk about. The first thing to notice is the notation. So discrete time stochastic process, of course, is a sequence of random variables, and likewise discrete time filtration generated by such a stochastic process is a sequence of sigma fields. So at time 0 there is f0 superscript x to denote that it's generated by x, and at time 1 the time index changes but the name stays the same, etc., etc. Now, when we're talking about random variables in a probability space, we always assume measurability. Okay, this means that x0, x1, etc., they are all f measurable. Remember, there's a sigma field present in this probability space. If our filtration fxn has the property that it's the smallest sigma field in some way, so that all of these random variables are measurable with respect to fxn at each time step n, well, they are also f measurable. And fxn is the smallest one, so it must be true that fxn is contained in my sigma field f for all n, and this is because of measurability. The other thing to notice is that, of course, if I have fxn and I compare it to fxn plus 1, of course, what is the difference between them? Fxn plus 1 is going to be the smallest sigma field, so that x0 up to xn, as well as xn plus 1, are all fxn plus 1 measurable. So what this tells us is that fxn plus 1 must be a bigger sigma field than fxn. It could be the same sigma field if the random variable xn plus 1 is constant, because constant random variables are measurable with respect to anything, but it is definitely not going to be any smaller. So it's certainly true that if we take a time step and we increase it by 1, then we will find that our sigma field gets bigger. This is a very interesting property. So we have a discrete time stochastic process, we have a probability space, then the filtration generated by my stochastic process is a sequence of sigma fields that satisfies these two properties. For each time step, the sigma field that I'm currently working with is contained in the big sigma field in my probability space, and as time goes on, these sigma fields are getting bigger and bigger in the sense that they are containing more and more events. Now, this sounds like something that would be really quite useful to have. For example, going back to our example of the FTSE 100 price index, of course, the information that's contained in the FTSE 100 price index doesn't just consist of the value of the index itself. This index is made out of the 100 most capitalized shares on the London Stock Exchange. And of course, each of those is a stochastic process by itself, and it moves up and down according to movements in the market, changes that are made by the companies connected to these shares, etc. So there is a lot of information that builds into the value of the FTSE 100 stock price index. So in fact, sometimes filtrations are not just generated by a single stochastic process, they might be generated by many, many other things. And this leads to a more general definition, and that is just a general discrete time filtration. A discrete time filtration in a probability space is a sequence of sigma fields, and the sigma fields have the property that each of them are contained in my master sigma field f of the probability space capital omega fp. And as time goes on, these sigma fields are getting richer and richer in the sense that more and more events are added to the sigma field in each case. If we have a probability space, then it's so common to attach a filtration to a probability space that we actually have a special name for it. If we have a probability space and we attach a filtration, we have 4 objects that we can group together, and we call them a filtered probability space. Now, the next thing that we need to talk about is we need to talk about how to connect discrete time stochastic processes to discrete time filtration. It's very nice if a stochastic process X generates a filtration, because then you know immediately if you have the nth component of your filtration, fxn, then all the values of your stochastic process X up to time n will be fxn measurable. So it'd be nice to have similar kind of connections between just a general filtration and a stochastic process. And this is what this next bit is about. So let me create some space for us and then we can talk about that. So more generally, suppose now that we have a discrete time stochastic process X, and we have a probability space together with a filtration, which is of course a filtered probability space. Then there are two important notions that we need to talk about for now. The first notion is adaptedness, and this is something that's going to be really important. Our stochastic process X is adapted to our filtration if for each n, my current random variable attached to my stochastic process xn is measurable with my current sigma field in my filtration fn. Of course, remember that measurability simply means that the sigma field generated by xn must be contained in fn. And my filtration generated by X has this property that it's the smallest filtration with the property that xn is measurable with respect to the current sigma field attached to that filtration at time n. So this is important enough to write down, so let me do that. Adaptedness means that if a stochastic process is adapted to a filtration, that filtration contains all of the information that we can get from the stochastic process as it evolves over time. And the smallest filtration that contains this information is the filtration generated by the stochastic process. And for that reason, the filtration generated by a stochastic process is actually also called its natural filtration. And I don't believe I wrote it down, so let me do this. Okay, so that is adaptedness. There's another notion that we use very often in finance, so it's worth knowing about it, and that's predictability. So we talked about adaptedness, and adaptedness means that given the current sigma field in the filtration, you have all the information you need to know about the current value of your stochastic process. Now, predictability means that if you know the current value of your sigma field in your filtration, then you can actually say what the value of your stochastic process is going to be one step in advance. So literally, it means that your process is predictable given the information that you get over time. And mathematically, we express this by saying that the stochastic process, and notice here it starts at 1 and not at 0, because we don't actually depend on x0 in this definition. It is predictable with respect to the filtration if for each n, xn is actually fn minus 1 measurable. So it's measurable one step in advance. And that literally means if you have knowledge of the sigma field fn minus 1, you have all of the information that you need to be able to determine the value of your stochastic process at the next step. Now, this is very important in finance because very often we make financial decisions in advance. Well, let me go back to the evolution of the FTSE 100 and show you what I mean. Okay, suppose that I want to make an investment that's connected to the value of the FTSE 100. Well, I will make that decision now, and then probably I will buy some shares or sell some shares now, and I will hold on to them for a little bit, won't I? So what do I do if I want to calculate the value of my portfolio in advance? Well, I will simply go number of shares multiplied by the share price. The number of shares I already know. This is measurable with respect to the sigma field that is active at this very moment. However, the share prices or the value of the FTSE 100, that's going to evolve over time, and I don't know what that is yet. Typically in finance, what we see when we are working with portfolios is that we get a mixture of adapted and predictable processes. Typically, if you have a portfolio or a trading strategy, your holdings will be predictable. However, the values of your assets will actually be adapted, because that depends on stock prices or the values of indices, and those things become measurable as time evolves, whereas your portfolio holdings, you typically decide a little bit in advance, and therefore that tends to be predictable.